This video is to show you how to get your average, standard deviation, and t-test using just Google Sheets. For a lot of your experiments, you're going to have to calculate those basic statistics, and it's luckily fairly straightforward with the regular Google Sheets functions. If you can, still try to get Excel Minor Tool Pack. Not very many students are able to get that these days, but I would definitely suggest doing that, Excel Minor Tool Pack. But if you can't get that, let me show you what you're going to do. So to get the average is probably the easiest thing. You're just going to click underneath. So this is an example. Say a student grew 10 plants and grew 10 of them, watering them with sparkling water, and another 10 using faucet water. They're interested to see how that affected their growth. So to get the average, you want to click right underneath. Working, I think it is. Okay. Click underneath the row or the column of numbers. And you want to click on this backwards E. This is the sum or the sigma Greek letter there, but you want to click average right here, and it will then say, what do you want to average? And then you say, well, I want to average these 10 numbers. So highlight those 10. Click and drag and highlight, and then release, and it should pretty much already calculate. See, it says 26.1. Hit enter, and it'll show you what that average is. Then you want to average the faucet water, and instead of even doing that again, you just want to hover until you see this black cross cover this blue square. Click and hold and drag to your right, and it'll copy that function to the next column over. So boom, insto presto, you have both average numbers. Now, standard deviation is important because it tells you how variable those numbers are. Like, are they really spread out from the mean, or are they very similar, very close to that mean? Very tight. For example, are they all close to 26, or are they like 40, 5, and then all over the place? Are they close to 36? Are they like 37, 38, 34, 35, or are they all over the place? So to do that is a little more involved. Say click in this box where you want to get your standard deviation. Then you want to go to insert function, and then down to statistical, and then look at all the stuff you can do. This is awesome. It feels kind of scary, but it's actually exciting. Look at all these statistics you can run. And you want to go to where the S's are, because that's going to be your standard deviation. Boom, you see STDEV, standard deviation. Click on that, and it should say standard deviation of what number. See, you got to tell Sheets what to do. So you want to highlight your 10 numbers. Do not highlight the average, okay? And see, it tells you already 13.27. So I have my 10. I'm making sure it's just those 10 highlighted. I release, and then I hit enter, and boom, it gives me my standard deviation. And what I'm going to do is, like I showed you before, click in the square or in the cell, hover with your black cross over the blue square, click and hold, drag over. It's going to drag that function. So immediately I see, that's a pretty big difference. Well, I don't know. It's not that big actually. But we got 13.3 rounded standard deviation for sparkling water and 9.6 or 10. That means that the faucet water numbers are more centered around the average. So this right here, the faucet water, those are more reliable because they have a lower standard deviation. Lower standard deviation equals more reliable. Okay, the lower it is, the more reliable. I trust that average more because those numbers were in total closer to that average. And that's something you're going to have in the human physiology, the lab stations lab is going to ask you that in a lot of different things. So very important statistic. You will also use standard deviation for your error bars when you do a bar graph of all your data. So if I made a bar graph of this, 1 bar for sparkling water, which is 26, 1 bar for faucet water, which is 36.6, I would use my standard deviation, add it to and subtract it from my average to get my error bars. So I'm going to put that here, used for error bars. And what you add and subtract from average. Okay, so you're going to have 9.65 above the faucet water and 9.65 below. So it's going to be equal. 9.65 up here, 9.65 up here, 9.65 below. All right, now one of the most important things we can do are t-tests, or as you might see in some other videos, the ANOVA, which is basically seeing if these averages are significantly different. Faucet water, it's a bigger average, right? It's bigger than the sparkling water. But is it really meaningful? Because if we have any two studies, two sets of data, and we get the average, you're never going to get exactly the same result. It's always going to be different. And if it isn't different, that's a problem in itself. So is that difference meaningful? I'm going to type that in here. Is the difference And in statistics, we call that significant. Is it a meaningful difference? Is it a significant difference? So to get that, to find that out, we will click in the box wherever we want it to show up, and we go to Insert, Function, Statistical, and we want to go to t-test. There's a bunch of t's here. I get confused with the t-distribution sometimes, but you want to look at t-test, and then you'll see this box pop up. And what you want to do is highlight your first set of data, which is the sparkling water. So I'm going to highlight the 1 through 10 plants, and then let go of the button. Then I click comma. So C5 through C14, looking at my row, C5 good, 14 the row and column, that looks good. Now I want to compare that to my faucet water, so I'm going to highlight my faucet water, let go of the button, boom, it's there. D5 through D14, that looks good. Then important, I got to put a comma, and I got to put a 2 for 2 degrees of freedom, or actually 2. I'm looking at either t-test, look at the distribution on one side or on both sides of the average. So I'm going to be looking at both sides, which means two-tailed. And then also I'm going to put another 2, meaning there's 2 possible outcomes. So you will always use 2 and 2 after your after you highlight the 2 columns. So that should be good. And see, it already gives it to me, 0.058. So I'm pretty close. I hit enter, and then it pops that number in. And when you look at that, if that number is less than 0.05, then it's significant. Significant. So if it's less than 0.05, it's significant. If it isn't, it means it is just due to chance. If it is greater than 0.05, so it's due to chance. So as you might see, this is greater than 0.05, so this would not be significant. Our results are not significant. Our p-value, we would say our p-value is not significant. And this means we accept the null hypothesis that sparkling water and faucet water do not make an impact on the growth of plants. We accept. Second. We accept the null hypothesis. That sparkling water and faucet water have the same effect on the growth of plants. That's always what our null hypothesis says. It says there's no real difference in, whatever we're doing here, we're influencing the water that we're using. Whatever you're doing, it's not having an effect. Now, the alternative hypothesis that we would have written beforehand maybe it said plants grow better or worse with sparkling water. Plants grow better or it could have been your hypothesis that it's worse. Okay, so if, for example, our null hypothesis was like 0.02, 0.0108, anything less than 0.05, we would reject the null hypothesis and then say that we accept our alternative hypothesis that changing the water significantly changed how well those plants grew. All right.